Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
You know the image. I mean, it's basically burned into our brains at this point. The pale blue dot.
Oh, yeah. Voyager 1, Carl Sagan's whole speech, it's iconic.
It is, right. That one tiny pixel of light just hanging there in a sunbeam.
Yes.
And for what, the last 30 plus years, that's been our shorthand for life in the universe. If you look for aliens, you look for the blue, you look for oceans, you look for that specific shade that says Earth-like. It's almost romantic.
It is. It's a beautiful thought. But it's also, it's a bit of a trap.
A trap? How so?
It's a cognitive trap because it locks us into looking for a mirror. We're looking for ourselves, but ourselves today. It just assumes that habitable always equals blue.
And that is exactly where we're going today.
Yeah.
I want you to just, for a second, reimagine that dot. Forget the blue. Instead, picture that pixel as a deep, vibrant purple.
Or get this, what if the oceans on that dot weren't blue at all, but like a bright, almost neon green?
And here's the kicker. This isn't science fiction. We're not talking about some far-flung alien world.
Yeah. No, not at all. We are talking about Earth. This is our own history. If alien astronomers had been looking at our planet at different times, they wouldn't have seen a pale blue dot.
They'd have seen a purple world.
Oh.
Or a green ocean world.
And that simple fact that our planet changes its color over billions of years is at the heart of this. Well, this really intense debate happening inside NASA right now.
It's a huge struggle. We're talking about giant space telescopes, billion-dollar budget fights, ancient bacteria, and even rocks that are trying to trick us.
Exactly.
We're looking at a new white paper that just came out, January 2026, on the ARTSIF preprint server. It's from the Living Worlds Working Group.
Which is a very, very cool name for a committee of scientists.
It sounds like a superhero team, doesn't it? But their job is actually really practical. They're trying to define the capabilities of the next great space telescope, the Habitable Worlds Observatory, or HWO.
Right. And the argument they're making in this paper is, to put it simply, if we build this thing on the cheap, if we cut corners on the sensors to save a few $1 billion,
Which always happens.
It always happens. Then we might stare right at a living planet and have absolutely no idea what we're looking at.
Or, and I think this might be worse, we might stare at a dead, toxic rock and convince ourselves we found a jungle.
That's the fear. That's the big false positive nightmare.
So that's the mission today. We're going hunting for purple Earths, green oceans, and the cosmic imposters trying to fool us.
Let's do it.
Okay, so before we even get to the cool biology, the purple bacteria and all that, we have to talk about the machine, the tool, this Habitable Worlds Observatory.
The HWO.
Yeah. I mean, we've all been obsessed with the James Webb Telescope, JWST, for the last few years. The images are just stunning. So why do we need another huge, expensive telescope? What can HWO do that Webb can't?
That is the multi-billion-dollar question, isn't it? And it really comes down to how they look at planets. JWST is an absolute marvel, don't get me wrong, but for exoplanets, planets around other stars, it mostly uses a method called transit spectroscopy.
Transits, okay, so that's the shadow method, right?
The shadow method, exactly. You have to wait for a planet to pass directly in front of its star from our point of view.
And as it does, a tiny bit of the starlight shines through the planet's atmosphere.
Precisely, like sunlight through a stained glass window. And by looking at what colors get filtered out, you can tell what gases are in that atmosphere. Oh, there's methane here, there's water vapor. It's incredible.
Like there's a but.
There's a big but. You're only seeing the edges. You're basically looking at a backlit silhouette of the planet. You're sniffing its air, but you're not seeing its surface.
I can't see the ground.
You can't see the ground. The Habitable Worlds Observatory is designed to do something much, much harder. It's designed for direct imaging.
Which sounds simple. It just means taking a picture of the planet itself.
It sounds simple. We take pictures all day, but the physics of it are just staggering. You're trying to photograph a tiny firefly floating right next to a giant blinding searchlight.
From miles and miles away.
From light years away. The star is billions of times brighter than the planet. If you just point a telescope, the planet is completely lost in the glare.
So how do you solve that? What's the trick?
The trick is a very clever piece of engineering called a coronagraph.
A coronagraph?
Yeah, think of it this way. If you're outside and the sun is in your eyes, but you want to see, I don't know, a bird flying near it, what do you do instinctively?
I put my hand up, block the sun with my thumb.
Exactly. You create a tiny artificial eclipse just for your eye. A coronagraph is a super high-tech hand inside the telescope. It's a system of masks and mirrors that physically block the light from the star.
So it creates a little shadow right where the star is.
A perfect little shadow. It suppresses that glare by an insane amount. Like, it blocks 99.99999% of the starlight. And suddenly the faint little speck of light reflecting off the planet next to it can actually be seen.
And that's the revolution. Because if you can block the star, you're not just seeing the atmosphere anymore.
Now you're seeing the surface.
You're seeing the light bouncing off the continents, off the oceans. You can actually see its color.
And that's where all the trouble starts. Because seeing color sounds easy, but to do it from that distance, you need incredibly clean data. The whole point of this new white paper is that the HWO needs an exceptionally high signal-to-noise ratio.
Signal-to-noise, we talk about that in audio production, so it's about clarity.
It's all about clarity. It's not just about getting more light, it's about getting clean light. Imagine you're at a really loud concert and someone across the room is trying to whisper a secret password to you.
Okay.
The loud music is the noise. All the stray light from the star, from dust in space, even heat from the telescope itself. The whisper is the signal, that little sliver of colored light that might indicate life.
And if the signal-to-noise is low, the music is too loud.
You can't hear the password. You might hear a murmur, you might think they said the right word, but you can't be sure. The scientists are saying they need a system so quiet, so sensitive, that they can pick out that whisper with total confidence.
And this gets us back to the horse trading you mentioned. Because making a quiet telescope is expensive.
Unbelievably expensive. Every little bit of improved performance costs millions or tens of millions. And the financial managers at NASA, their job is to look at the plans and say, okay, do you really need the deluxe sensor package? Can't you just make do with the standard one?
Can't you just, fix it in Photoshop later?
Exactly. And this paper from the Living Worlds group is their response. It's them saying, look, this isn't a luxury feature. This isn't just gold plating. If we don't have this specific capability, the entire mission could fail. We won't be able to hear the whisper.
Okay, so let's get into what they're trying to hear. What's the whisper? If an alien astronomer is looking at Earth right now, what's the gold standard signal that screams life?
For modern Earth, the clearest, most unambiguous surface biosignature is something called the vegetation red edge.
The red edge. It sounds like a spy movie.
A cliff is actually the best way to think about it. So we all know plants are green because chlorophyll absorbs red and blue light for photosynthesis, right?
Right, and it reflects the green light, which is why we see it as green.
But that's not the whole story. There's something else happening that our eyes can't see. Plants are also reflecting a huge amount of near-infrared light.
Okay, why? What's the evolutionary advantage there?
It's a radiator. It's thermal regulation. Infrared light is basically heat. If plants absorbed all that infrared energy from the sun, they'd literally cook themselves from the inside out.
Ah, so they need to get rid of it.
They need to get rid of it fast. So they evolved this amazing trick where their cell structures act like perfect mirrors for near-infrared light. They just bounce it right back into space.
That's genius.
It is. And if you plot this on a graph of light, a spectrogram, it creates this incredibly dramatic feature. The brightness is low in the red part of the spectrum because the plants are eating that light. And then as soon as you cross over into the near-infrared, boom, the line shoots straight up like a vertical wall.
A cliff.
A cliff. That sharp, sudden jump is the vegetation red edge.
And rocks don't do that.
Rocks and sand and dirt, they don't do that. Their reflection spectra are usually smooth slopes. They don't have sharp edges. If you see that cliff, it's one of the strongest signs of widespread complex life you could ever hope for.
But, and I'm sensing the catch here, the thing the white paper is worried about, you can only see that cliff if your camera can see into the infrared.
There's the catch. If the budget committee says, hey, those near-infrared sensors are too complex, too expensive, let's just stick to the visible light our eyes can see, then you completely miss the red edge.
The cliff is invisible to you.
It's invisible. You could be looking at a planet covered in the Amazon rainforest and it would just look like a dark, unremarkable smudge. You miss the smoking gun.
So that's argument number one for the expensive model. We need infrared to see Earth-like life today. But the paper goes deeper, doesn't it? Because looking for modern Earth isn't enough.
Not even close. I mean, this is where it gets really mind-bending for me. We're so biased towards green chlorophyll, but chlorophyll is, in the grand scheme of things, a fairly recent invention. For a huge chunk of our planet's history, the world wasn't green.
It was purple.
It was purple.
The purple Earth hypothesis.
Oh.
I love this. So take us back. What's going on purple Earth?
We're talking maybe 3 billion, 2.5 billion years ago. The most advanced life forms on the planet were these single-celled organisms, purple anoxygenic phototrophs.
Okay, that's a mouthful.
It is. Let's just call them purple bacteria. The key thing is they didn't use chlorophyll for photosynthesis. They used a different kind of pigment called retinol.
Retinol, wait, as in the stuff in our retinas, in our eyes.
Very, very similar chemical structure. The same pigments your eyes use to detect light, these ancient bacteria used to harvest energy from the sun.
Yeah.
And they work differently from chlorophyll.
How so?
Chlorophyll absorbs red and blue, reflects green. Retinol is basically the opposite. It's most efficient at absorbing green and yellow light, which, by the way, is the peak of the sun's energy output.
So it's absorbing the most powerful part of the sunlight. And if it absorbs green...
It reflects the other parts. It reflects red and blue light.
And if you mix red and blue paint, you get...
You get purple, a deep, rich purple.
So for 1 billion years, maybe more, any continents or shallow coastal areas on Earth would have been covered in these vast purple mats of bacteria.
And this isn't just a theory. We still have them. If you go to super salty places like the Great Salt Lake or certain salt flats, you can see these organisms called halobacteria. They turn the water this shocking, brilliant pink or purple color.
So we can see what ancient Earth looked like today.
We can. And here's the number from the paper that just fools me. This purple Earth phase might have lasted for nearly 1.5 billion years.
That's staggering. That's more than twice as long as complex animals have even existed.
Exactly. For a huge percentage of the time that Earth has been alive, it was a purple planet. So now apply that to the telescope problem.
Okay, so if HWO is scanning the galaxy and it finds a planet that happens to be in its own purple phase right now,
What do we see?
well, if we don't have the right sensors, we see nothing.
We see nothing. These purple bacteria, their retinal pigments, they absorb light well into the infrared.
Okay.
So their spectral signature, their edge, is different from chlorophyll's. If we build a telescope that is only looking for the red edge of modern plants,
We're wearing the wrong color glasses.
you're wearing the wrong glasses, you would look at a world that is absolutely teeming with life, a thriving global biosphere, and your multi-billion-dollar instrument would tell you it's a dead rock.
That is the ultimate nightmare scenario. We spend 20 years building this thing, point it at a second Earth, and just completely fail to recognize it.
That's the argument. The Living Worlds Working Group is basically screaming, you cannot design this machine just to find us today. You have to design it to find who we were yesterday. Because statistically, for any given planet, it might be more likely to be in its purple phase than its green phase.
Okay, so we've got purple Earth. But the story doesn't just jump from purple to the green forest we see today. There was an intermediate step in the outline,
There was a middle chapter, the green ocean hypothesis.
where the oceans themselves turned green.
Yes, this is a fascinating period, geologically and biologically. We're talking about the Archean eon, so maybe between 4 and 2.5 billion years ago. The world was different. The atmosphere had no oxygen.
So what made the water green? Was it some kind of early algae?
No, not at first. It was the rock, the planet's geology. The oceans were full of dissolved iron that was being pumped out of hydrothermal vents on the seafloor, specifically ferrous iron.
And that colors the water.
It does. Ferrous iron in a solution is really good at absorbing light at the blue and red ends of the spectrum, but it doesn't absorb green light very well.
So it reflects the green. The ocean itself, just the water and iron, would have looked green.
That kind of murky olive green, probably. But then life adapts. Evolution is always an opportunist. You have these early cyanobacteria floating in the water. They need sunlight. But the water they're living in is filtering out all the good red and blue light.
So the only light that's making it down to them is the green light that the iron isn't absorbing.
The leftovers. So what do? They evolve a new tool. They develop special accessory pigments called phycobilins that are perfectly tuned to capture and use green light for photosynthesis.
It's like they're tuning their antenna to the only radio station that's broadcasting.
Perfect analogy. And so you get this layered effect. You have a geological green signal from the iron, and then a biological green signal from the bacteria living in it.
Now, from the telescope's point of view, that's got to be confusing.
It's extremely confusing, because if you just look at the overall color, a planet with a green ocean full of cyanobacteria looks very, very similar to a planet with continents covered in green forests.
So if we saw that, would it even matter? I mean, green is green, life is life, we pop the champagne, right?
I mean, yes and no. On the one hand, any robust green signal is a huge deal. But scientifically, we'd want to know what we're looking at. Is this a primitive, oxygen-poor world with simple bacteria?
Or is it a mature, oxygen-rich world with complex plants?
Those are two fundamentally different stages of planetary evolution. Telling them apart requires incredibly high spectral resolution. You need to be able to see the subtle little bumps and wiggles in the spectrum that differentiate a phycobilin pigment from a chlorophyll pigment.
So again, it comes back to the quality of the instrument. Don't give us a blurry, low-res camera.
Exactly. But it gets even more complicated, because sometimes a color that looks like life isn't life at all. Sometimes it's just a rock trying to fool you.
This is the part that gives me anxiety. The mimics, the false positives.
This is the core of the engineering argument in the paper. It's about being sure. We are so desperate to find life, there's a huge risk of confirmation bias. We want to believe. The universe, however, is full of minerals that can look an awful lot like biology.
So let's go through the list of suspects. What's mimic number one?
The most obvious one is iron oxide. Rust.
Mars.
Mars is the poster child. It's the red planet because it's covered in rust. Spectrally, rust creates what's called a red slope. It just reflects more and more light as you go from green to red to infrared.
And if you have a blurry instrument, a gentle slope can look a lot like a sharp edge.
They can blur together. Think about looking at a ramp versus a single step from really far away. If your vision is bad, they can look the same. You could absolutely mistake a dead, rusty desert planet for a world covered in vegetation.
So how do you tell them apart?
You need high resolution. You need to be able to see the sharpness of the feature. Biology creates sharp, well-defined edges. Geology is usually smoother, more sloped. You need an instrument that can tell the difference.
Okay, so rust is a big one. But the paper mentioned another mineral that was much more exotic. Cinnabar.
Cinnabar, yeah. Mercury sulfide, it's this brilliant red mineral.
And it's mercury. It's incredibly toxic.
You would not want to land on a planet made of cinnabar. But here's the universe playing a cruel joke on us. Cinnabar has a spectral feature. It has a very strong, very sharp, reflective edge.
It's like plants do.
Just like plants. But there's one tiny critical difference. The vegetation red edge happens at a wavelength of about 700 nanometers.
Okay.
The cinnabar edge happens at about 600 nanometers.
That's 100 nanometers. That sounds like almost nothing.
It is almost nothing. And if your telescope has low spectral resolution, if your pixels are too fat, then 600 nanometers and 700 nanometers can fall into the same data bin. They blur together into one signal.
So imagine the press conference. NASA gets up and says, "We found it. A planet with a clear biological edge. It's covered in red forests."
And then 10 years later, a better instrument goes up and we realize, oh, whoops, it's actually a giant poisonous mercury rock.
That would be devastating.
That is the nightmare. That is why they are fighting for this high resolution. They're saying we have to be able to tell the difference between 600 and 700 nanometers with absolute certainty. We need to be able to distinguish a tree from a toxic rock.
Wow. Okay, and there was one more mimic, right? Sulfur?
Elemental sulfur, yeah. It has its own edge, but it's down around 450 to 500 nanometers. It's a little easier to spot because it's further away from the vegetation signal, but the principle is the same. A planet could have a weird mix of minerals, maybe some sulfur and some cinnabar.
And with a low-res instrument, that combination of signals could mash together into something that looks convincingly and incorrectly biological.
You got it. It's not that the universe is intentionally trying to trick us. It's just that chemistry is complex. And biology is just a very specific, very organized form of chemistry. To find it, you need tools that are precise enough to measure that specific organization.
So this all brings us back to the present day, to the horse trading. We have this paper, a scientific argument, but it's a negotiating tool.
It's absolutely a negotiating tool. The Living Worlds Working Group is laying out its case for the budget committees at NASA and in Congress.
And the case is basically, if you cut our budget and force us to buy the cheap camera,
we will confuse mercury for forests. We will miss entire purple biospheres. The mission you're paying for will not be the mission you get.
So what's the wish list, summed up?
It's 3 things. 1, high signal to noise so we can actually see the faint light from the surface. 2, Wide spectral range from visible light through near-infrared, so we can see both the red edge and the signatures of purple Earths.
And 3.
High spectral resolution, so we can tell the difference between a real biological edge and a geological mimic like cinnabar.
And what's the reality? What's likely to happen? The sources mention recent cuts to other big NASA programs.
The reality is that the budget is extremely tight. It's very unlikely they'll get everything on their wish list. There are going to be compromises.
But the compromise here feels so much more significant than, getting a slightly smaller hard drive.
It is. A compromise here fundamentally changes the nature of the mission. It takes you from a mission of discovery and confirmation to a mission of discovery and ambiguity.
And nobody wants to spend 20 years and $10 billion just to get a maybe.
Exactly. To spend all that time and effort to point to a pale purple dot and say, well, that might be life, but it also might be a rock, that would be an excruciating result. The scientists are arguing it's better to build the yes or no machine, even if it costs more upfront.
Because we might only get one shot at this.
We will only get one shot at this in our lifetimes. This is the flagship observatory for the next generation. We are building the eyes that our children and grandchildren will use to explore the galaxy.
And if we build them with cataracts on day one to save a bit of money, they're going to be the ones squinting at the blurry data.
That's the stakes. This paper is a plea to look at the long game.
So we've gone all the way from the pale blue dot to purple bacteria, green oceans, and toxic mimics. It's a much more complicated picture of what life might look like.
It really is. It shows that to find life out there, we first have to really, really understand the deep history of life right here.
We have to remember our own purple past.
And we have to be open to the idea that pale blue is just one outfit in a very large cosmic wardrobe.
So as we wrap up, I want to leave everyone listening with a final thought on this. We always talk about the cost of these huge projects. Billions of dollars for a telescope.
That's a lot of money.
It is. But think about the cost of not doing it right. Imagine we build the cheaper version. We scan 1,000 worlds and we find nothing but ambiguous smudges. We might conclude we're alone.
Right. We'd get a null result and just assume there's nothing there.
But what if we weren't alone? What if the galaxy is filled with purple worlds and we just didn't buy the right pair of glasses to see them? What's the higher cost? The cost of the telescope or the cost of staying alone in the universe when we didn't have to be?
Yeah, that's the question.
To look right at a living planet and see a dead rock because of a budget decision made decades earlier. I mean, that feels like a tragedy on a galactic scale.
The ultimate missed connection.
Here's hoping the Living Worlds Working Group wins their fight. Thanks so much for walking us through all this.
My pleasure. Keep looking up. And maybe look for purple.